Armed with the transpose convolution, you're now ready to dive into the details of the U-Net architecture. In this video, let's first go over the architecture quickly to build intuition about how the U-Net works, and in the next video, we'll go through the details together. Let's dig in. Here's our rough diagram of the neural network architecture for semantic segmentation. And so we use normal convolutions for the first part of the neural network. And similar to the earlier neural networks that you've seen, this part of the neural network will sort of compress the image. You've gone from a very large image to one where the height and width of this activation is much smaller. So you've lost a lot of spatial information because the dimension is much smaller, but it's much deeper. So for example, this middle layer may represent that looks like there's a cat roughly in the lower right hand portion of the image, but the detailed spatial information is lost because the height and width is much smaller. Then the second half of this neural network uses the transpose convolution to blow the representation size up back to the size of the original input image. Now it turns out that there's one modification to this architecture that would make it work much better, and that's what would turn this into the U-Net architecture, which is that skip connections from the earlier layers to the later layers like this, so that this earlier block of activations is copied directly to this later block. So why do we want to do this? Turns out that for this, next to final layer to decide which region is a cat, two types of information are useful. One is the high-level spatial, high-level contextual information, which it gets from this previous layer, where hopefully the neural network will have figured out that in the lower right-hand corner of the image, or maybe in the right part of the image, there's some cat-like stuff going on. But what is missing is a very detailed, fine-grained spatial information, because this set of activations here has lower spatial resolution. The height and width is just lower. So what the skip connection does is it allows the neural network to take this very high-resolution, low-level feature information where it could capture for every pixel position how much furry stuff is there in this pixel, and use the skip connection to pass that directly to this later layer. And so this way, this layer has both the lower resolution but high-level spatial, high-level contextual information, as well as the lower level but more detailed texture-like information in order to make a decision as to whether a certain pixel is part of a cat or not. In this video, you saw just a brief high-level intuition about how U-Net works. Let's go on to the next video to see the details of how you can implement it.